Okay, this is part 2 of a video series on a pretty standard physics problem involving currents and magnetic fields. So if you've not watched part 1 of this video, I would encourage you to go watch that first. This is going to be a short video talking about why we're going to use the force per unit length. So what I have here is part of the drawing for the previous problems to remind you what that looks like. I have a couple of currents sitting at the vertices of an equilateral triangle, and I have found the field at the third vertex. So now what I'm going to do is I'm going to put a current at the third vertex. I've called it I3. Remember, there's a current I1 from which B1 arises, a current I2 from which B2 arises. I now have placed a current I3, and it's a little hard to see because the graphics are getting a little crowded, but this current is coming out of the page. Yeah, it looks like there's an X here. Let me just fix this, just so it's clear. This current is coming out of the page. It looks like there's an X because of the triangle and the circle. I3, sorry, is coming out of the page. So the question now is, what force is exerted on I3 on the wire due to the magnetic field? So here's the formula, or at least for the magnitude of the magnetic force of a current carrying wire sitting in a magnetic field. ILB sine of theta. You should recognize this as the coming from a cross product. This is the magnitude of that force. The actual force would be given by a cross product, which we're going to take care of by finding the magnitude and then using the right hand rule. But remember what this is. I is the current that's sitting in the field. L is going to be a vector directed along the current. In most cases, it's going to become the length of the wire. And B is the field in which the current I is sitting. And sine theta, theta is the angle between the L vector and the B vector. So that's all well and good. But what happens if A, you don't know how long your wire is, or B, you have what is in all practical purposes, for all practical purposes, an infinite wire? The length here is not going to make a whole lot of sense. In this case, the current is coming into or out of the page. It can be coming out of the page into the page. Regardless, I don't know how long that wire is, and so L is going to be a problem. My strategy, which turns out to be a much more useful quantity than just the force, is to divide it out. So I now have this expression, not for just the force, but for the force per unit length. Okay, in this case, I've substituted in my specific I3. The B field is going to be the total field that I got in the previous part of the problem with the vector summation of B1 and B2. Although in the next video, we're going to solve this as it is from scratch. We're going to find the force due to this field, the force due to this field, and add them vectorially so that you can start here. But if you've already solved for the total B field, you'll be able to plug it in just directly, but we'll do it the long way for now. The sine of theta here is going to be 1. Theta, these are orthogonal, so the sine of 90 degrees is just 1. And that's the force per unit length, which we'll see more of in the next video.